Hello everyone, this is an introduction to the concept of determinants. Let me explain what a determinant is. Just remember that if you have a 2 by 2 matrix A, B, C, D, then there is a criterion for invertibility of that matrix, which is the following. If you define D to be AD minus BC, then if that quantity is non-zero, then there is a formula for the inverse matrix, which is given by this expression. So that number right there determines whether the matrix is invertible, and that is an important quantity, which is called the determinant of the matrix A. So what I would like to do is actually find a similar quantity for the invertibility of a 3 by 3 matrix. Is that possible? So in particular, what I would like is if I have a matrix A, B, C, D, E, F, G, H, I, then can we have some easy, relatively easy numerical condition that determines invertibility. Invertibility. So is just something that plays the role of the determinant in a 3 by 3 case. So there is such a thing. So let's see how we can come up with it. How did we come up with the condition for a 2 by 2 matrix? Well, it comes from the condition that for an n by n matrix A, uh, that matrix is invertible if and only if an echelon form of A, any echelon form, for example, the row reduced echelon form, has exactly n pivots. So suppose that I have a 2 by 2 matrix, A, B, C, D, and I want to know if there are n pivots, in this case, 2 pivots. Well, if both A and C were 0, then there would be no pivot in that column. So there are no pivots. There's no 2 pivots, so it's not invertible. So one of the two has to be non-zero. I'm going to assume that A is non-zero. Otherwise, I would know that it is already not invertible if both A and C were 0. But let's assume that A is non-zero. Then I can row reduce, and the row reduction looks like this. If I try to multiply the first row by a multiple so that I eliminate that C, I'm going to get, this is what I get. You can work it out yourself. This is what happens in the row reduction. And then if I try to row reduce some more, then I can multiply by A, the second row, just to simplify, so I get a cleaner expression. And what I get is this expression. So I had assumed already that A is non-zero, so I'm going to have 2 pivots if and only if AD minus BC, this quantity right here, is non-zero, so that is a pivot. So that is one way to come up with that condition. So let's try the same thing, but in the 3 by 3 case. I'm going to try to row reduce a 3 by 3 matrix to the identity and see what that tells me about pivots. Okay, so let's try the 3 by 3 case. I start with A, B, C, D, E, F, G, H, I, and I'm going to try to reduce it to the identity. Once again, I can assume that one of these three numbers, A, D, G, is non-zero, and I can proceed in different ways if A was 0 but D was not, but let's just, for the sake of this argument, that A is non-zero, so that the very first element here is going to be a pivot. Otherwise, I can also switch rows if necessary. So now I have A, B, C. The row reduction looks like this when I eliminate that this entry and this entry in the row reduction, the coefficients that I get look like this. And when I row reduce to eliminate this coefficient over here, the coefficient that I get here is like this. Okay, if you do the row reduction, then with letters in these variables, then you'll see that the matrix ends up looking exactly like this. Okay, and then do one more row reduction. What we're going to do now is I'm going to multiply both the second and third row by a to simplify the expressions here. I get a, b, c, 0, a, e minus b, d, a, f minus c, d, 0, a, h minus b, g, a, I minus c, g. And again, I'm going to assume that this is going to be a pivot so that that condition is met, that that is non-zero. So I'm going to assume again that this number here is non-zero and then continue from there. And then what I'm going to get is, I get this very impressive expression. I get this, and then b a e minus bd. In this, I eliminate this entry, and then what I get is AF minus CD. And the expression that I get here is AI minus CG minus AF minus CD times AH minus BG divided by AE minus BD. Okay, so if there's going to be 3 pivots, then this expression here must be non-zero. So if there's going to be 3 pivots, we must have that AI minus CG minus AF minus CD times AH minus BG divided by AE minus BD is non-zero. And if I multiply through by this denominator, I get A. So I get that AE minus BD times AI minus CG minus AF minus CD AH minus BG is non-zero. And this simplifies to the following expression: A times EI minus FH minus B times DI minus FG plus C times DH minus EG is non-zero. And this quantity is what I'm going to call the determinant of the 3 by 3 matrix A that we were working with. So this number is going to be the quantity that is going to determine whether the matrix is invertible. And note that this determinant is A times a determinant of E, F, H, I minus B times a determinant of D, F, G, I plus C times a determinant D, E, G, H. So let me reinterpret those numbers as follows. What are those numbers? Where are these expressions coming from? Well, remember that I have a matrix A, B, C, D, E, F, G, H, I. And then what we are doing is let me do it like this. So I'm going to take A, and then look at what's left. If I cross out the row and column where A is, I'm left with what we call a minor, a smaller matrix that is EFHI, which corresponds to this submatrix here. So it's A times this determinant. And then if I write again A, B, C, D, E, F, G, H, I, and pick B and cancel out the row and column where B is, I'm left with DGFI for columns, which is this determinant. And then if I do again but for C, and cancel out the numbers in the row and the column where the C is, I'm left with a minor DEGH, which is the matrix that appears here. So those matrices, the matrix that appears here, which is EFHI, is called the A11 minor of the matrix, and it's the matrix that I get when I cancel out the row and column where A11, where this coefficient is. That's the matrix that I get. And from here, what I get is the matrix DFGI, and this is called the A12 minor, which means that I take the coefficient that is in the first row, second column, eliminate those numbers, and the matrix that is left, that is called the A12 minor. And from here, I get the A13 minor, which is the matrix DEGH. And that's what happens if it's a 1-3 minor, I take the coefficient that is in the position first row, third column, cancel the first row, cancel the third column, and whatever is left, the rest of the matrix that is left, that is called the minor of the matrix. So this formula gives me a way to compute determinants of 3x3 matrix. This is 3x3 matrices, and let me compute with this formula right here. Let's compute the determinant of a matrix and see what happens. So for example, let's compute the determinant of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. It will be, this expression that we got is the expansion along the first row is called. So it is the first element of the first row, 1 times the determinant of the leftover minor, so 5, 6, 8, 9. Then it is alternating, so now it's minus 2 times, this 2 is whatever coefficient is there in this first row, second column, determinant of the minor that is left. So if I cancel those, I get the 4, 6, 7, 9 minor plus 3. This 3 is this coefficient times the matrix, the minor that is left. When I cancel out the first column and the first row and third column. So the determinant of 4, 5, 7, 8. If we calculate this is 1 times 9 times 5, 45 minus 48 minus 2 times 4 times 9, 36 minus 42 plus 3 times 4 times 8, 32 minus 7 times 5, 35, which is minus 3 plus 12 minus 9, which is 0. And that means that A, this matrix A, is not invertible. Because according to what we have shown before, the row reduction of this matrix will not have 3 pivots. So this matrix is not invertible. More generally, we can define a determinant just like we have done it in the 3x3 case and in the 2x2 case. We define the following. So let A be a matrix, be an n by n matrix, and let the determinant of A be A1 times the determinant of the A11 minor minus A12 times the determinant of the A12 minor plus minus 1 to the n plus 1 A1n times the determinant of the A1n minor, where Aij is the minor matrix obtained when we remove the ith column and the jth column of A. So let me show you what that looks like. By the way, this formula right here is what we call the expansion along the first row, because I am going along the first row with just looking at the coefficients of the first row and then looking at minors. But you can do this along, in fact, any row and any column, and you actually get the same answer. So let's find a determinant of in a particular example. For example, let's find the determinant of A, which is 1, 0, 2, 0, 0, 1, 3, 0, minus 1, 2, 0, 1, 1, 1, 0, minus 1 along the first row. So this is going to be the determinant of A is going to be 1 times the determinant of the minor that I get when I eliminate the first column and the first row. So this matrix, so it's going to be times the determinant of 1, 3, 0, 2, 0, 1, 1, 0, minus 1, minus 0 times a determinant of another minor, but it doesn't matter because it's multiplied by 0, plus 2 times the determinant of the minor that I get when I eliminate the first row and the third column. So I get 0, 1, 0, minus 1, 2, 1, 1, 1, minus 1, minus 0 times the determinant of another minor. In this case, it would be the determinant that I get in this 3 by 3 matrix, but it's multiplied by 0, so it doesn't matter. Okay, so now I need to figure out what are the determinants of these 3 by 3 matrices. But the determinants of these 3 by 3 matrices, I can actually do it sort of by hand. This is I can expand by the first row, and this will be 1 times this determinant, but there's a column of zeros, so that's going to be zeros. 3 times this determinant, so that will be non-zero, and 0 times this. So it's going to be overall is going to be minus 3 times minus 2 minus 1. So this determinant is that, and then plus 2 times this determinant, which if I expand again by the first row will be 1 times the determinant of this matrix that I get there. So is, by the way, it's minus 1 times minus 1 times minus 1, which is 1, minus 1, which is 0. So this is 0, and this is minus 3 times minus 3. So the total is 9. So that is the answer. That the determinant is 9, and therefore this matrix is invertible because it is a non-zero determinant. And again, it turns out that the expansion of the determinant in terms of minors can be computed along any row or column of A, except that the signs that go with the which each minor are as follows. This position is plus, minus, etc. So this will be minus, plus, etc. And then this is minus, plus. So if you're going to compute a determinant, then you have to multiply the minors, the determinants of the minors, by the appropriate sign according to whatever row or column you are expanding along. So let me show you a matrix and a determinant. I'm going to expand it along 2 different rows. So for example, if I have the matrix 1, 2, 0, 3, 4, 0, 0, 0, 2, I can do this in two different ways. So if I do it along the first row, which is the first definition we had, the determinant would be 1 times 8 minus 0 minus 2 times 6 minus 0 plus 0 times 3 times 0 minus 4 times 0, which is, well, what's that total? That would be 8 minus 12 and then 0. So 8 minus 12, I get minus 4 as my answer. So what if I do it along the last column? Along the last column, that is pretty easy, and it's going to start with, remember that this is plus minus plus, so it starts with a plus, so it's 0 times the determinant of 3 times 0 minus 4 times 0, doesn't matter because it's at 0. Then the second entry is here, is minus 0 times a determinant, it doesn't matter what determinant I get because it's multiplied by 0, plus, and then a 2. 2 times this 2 comes from this entry right here, and then I have to multiply by the determinant of the minor that I'm left with. So the determinant of 1, 2, 3, 4, which is going to be, so this is total, is twice the determinant of 1, 2, 3, 4. So it's 2 times 4 minus 6, so it's 2 times minus 2, which is minus 4. So as I said, those have to agree, and I can expand it along the first row, along last column. As long as I keep track of the signs correctly, I can expand it along any row or column I want. And sometimes, as you see, it's beneficial to do this last column because there are 2 zeros there, or maybe along the last row because again, these zeros will make the computation much easier.